Hey, Rocky. Hey, Bernie. Get the hell out of here. Hey, everybody. I hope everybody's doing well. It's been a while since I put a video up. I've been regrouping a little bit. I've also got a couple of little projects going on, so I just wanted to give you guys a quick update of where we are. So, before we get to this this radio, we're going to just talk a little bit about the Ford Thunderbird 1966 radio that we put back together and restored. That's going to get listed on eBay for sale this week. Again, all proceeds, 100% of the proceeds, are going to go to St. Jude's Children's Hospital. And I will be posting a separate video with a link to that auction if any of you are interested in it. And I again appreciate the support all of you have given me during that series. It's been fun. I actually have another radio, same radio, that I'm going to restore as well. I'm not going to do a series on it, but I'm also going to be restoring that one. And I will also donate a portion of the proceeds of that sale to the St. Jude's Children's Hospital as well. So that's the plan there. I also want to congratulate Wayne Ocean, who won our 700 subscriber giveaway. So Wayne has received his meter, and appreciate Wayne, and thank you for watching the channel and supporting it. So let's talk about what I'm doing now. So I'm working on, obviously, this radio. This is a Fada P28A P22, and I think this radio came out in 1940. And this was a radio that we got from our good friend Rebel 11. I'm going to say it wrong, but I'll put it up here. Rebel 1159, I think. I'm not positive, but it's an AC/DC set. I love the dial on this thing. It's really, really unique. We'll take a close look at that. And it's a suitcase type radio. It's got a little leather case, which I'll show you in the next episode. But essentially, what the story on this thing is that somebody was in here. That's the problem. So I can't trust any of the wiring in this thing. So here's the original schematic. Let's take a peek at it. And you'll see here, because it's an AC/DC set, we'll get a little pointer. You'll see here that there's a switch right here. This is the power switch. And then there's a switch right here which goes between battery and AC. Okay? And that changes the circuit. Obviously, here's your 45 volts B plus and your A. So we've eliminated the battery. I'm not going to run this thing on a battery. I'm not going to restore it with a battery. So I've essentially eliminated that entire circuitry, including the switch. And all I did was I went into Photoshop and redrew the diagram. Right? I took out all that battery stuff because we're not going to use it. We're going to hardwire these connections so that it's an AC set. And here we go. So we're good to go. Now you'll notice this is not a transformer set, right? It's a direct chassis, All-American 5, essentially. Basically, we have a little bit of a problem here. So we need 35 volts for the rectifier tube, okay? Now, there's two things we could do. We can put in this 560 ohm resistor, which probably needs to be a little bit higher because voltage was only 115 back in these days. Anybody want a bird, if you can hear it? So we have another solution that we can do in place of this resistor. And you're going to ask, what is that? Well, I'm going to explain it to you. This was explained to me by Brendan, and it made a lot of sense to me. And once I get through explaining to you what it is, I'll explain why it's beneficial. All right? So let me get this all set up, and I'll be right back and show you. Okay, so what are we going to do in place of that resistor? Now, if we put a resistor here, which is typically what we do, this resistor is going to generate a lot of heat, right? It's going to generate a huge amount of heat, right? And we don't want that. And, typically you'll find these things also in the curtain burner cords, where there was a huge resistor buried in there, which would get hot, burn the house down, if you've ever heard that term. So there's something we can do in place of this, and we can put a pair of capacitors in there. And the terminology for that is capacitive reactance. So what you see here is a fan motor cap. All right, it's the value. I'll put a picture of it right here for you. The value is 3.5 microfarads, 450 volts, and it's at 50/60 hertz. And that's what's important about this, is the frequency at which it operates. That's what determines how these things work. So, how does it work? Well, basically, it's basically how it charges and discharges the capacitor at a certain frequency. It's the time that it takes the capacitor to charge and discharge which creates the resistance and the drop in voltage with no heat. So what does it look like inside this cap? Let's show you. Here's a piece of paper. So let's see how it works. So basically what happens is it's the way in which the capacitors charge and discharge at a certain frequency. And it's based on the time that it takes to do that. And that's what creates the voltage drop with no heat. Really, really cool concept. So let's draw it out. We'll take two capacitors. These are non-polarized. We don't need polarized caps for this. And they're connected like this. And let's assume we've got a positive here and a negative here. And in our case, these are 3.5 microfarads, 450 volts, and we're running at 50/60 hertz. So this is our frequency. Okay? There's a calculator that will tell us what our actual resistance will be. So let's assume we have 120 volts coming in here on this side. What we want to come out of this side is about 35 to 40 volts. Okay? We probably want to stay closer to 35 because the tube that we've got in this radio as our rectifier is a 35Z5 GT. So we need 120 volts coming in and we need 35 volts coming out. There's no transformer in this set. So these two capacitors, which is right here, that's what this is, this fan capacitor, will perform that voltage drop for us. Okay? Now, how does it really work? Well, it allows each capacitor to only charge on the half cycle of our 60 cycle line. Okay? So that makes it easier on the capacitors and makes for a much longer life in this application as well. The higher the value of the capacitors, the less voltage drop we get. So what do I mean by each capacitor to only charge on the half cycle? So let's take a look at it this way. Right? So this is what our AC looks like. Right? Essentially. Well, here's capacitor 1, and here's capacitor 2, and here's capacitor 1, and here's capacitor 2. So the first one is charging here, the second one is charging here. That's how it works. Let me show you the calculator for this specific application. Remember, we have 120 volts coming in, and we need 35 volts coming out. And we're going to be able to determine the amount of resistance that we get from this configuration of 3.5 microfarads at 60 hertz. So let me show you that now. Okay, so here's the website. I'm going to put the link to the website in the description of the video as well so you could try it. But essentially this lets us calculate the capacitive reactance. So let's zero in a little bit on the calculator. We'll take a peek at it. So our motor cap we know is 3.5 microfarads. We know our frequency is 60 hertz. All right, let's calculate. And you'll see here that our solution is about 758 ohms of capacitance. That's what we're going to get coming out the other end. Now notice, if we make this a 10 microfarad cap, for example, I told you before that the higher the capacitor, less the resistance. So let's make it a 10 and calculate. We drop down to 265 ohms. So it's definitely relative to the amount of capacitance. So now we know that we're going to have a 758 ohm resistor, essentially, on that line of 120 volts. Let's go take a look at the schematic again. Okay, here's our schematic. And you'll see the original design called for a 560 ohm resistor. Ours is 780 something, right? So why is it higher? Well, you got to remember, when this set was designed, it was designed to run at 115 volts, right? That's what they had back in 1939. It wasn't steady 120. So the calculation that was made was based on the lower voltage. Well, we're going to be a little bit higher, so we're better off coming in a little bit higher here. If I put all this together and find out that I'm not getting my 35 volts, or I get more than 35 volts, well, we're going to probably blow the tube out. But we'll be able to adjust it so I can get a different motor start capacitor, motor relay capacitor. So that's going to be the way this works. Again, we're going to put this right in line. So if we look at our chassis, we pull the shot back a little bit. Our AC is going to come in, go right through here, come right to the rectifier tube, which sits here, and then we've got our filter caps that we put in. Okay, so that's how that's going to work. And if you look at the schematic that we have here, here's the two filter caps that I just showed you, right? Coming out of pin 8 of the 35Z5 GT, and then we'll go up to the rest of the radio. The rest of this radio I have to go over every connection because someone, I don't know what they were doing on this thing, I'm not exactly sure, but someone was trying to do something. If you recall, when I first put this radio on YouTube, someone had attached a switch, a potentiometer, directly to this coil. I'm not sure what they were trying to do and what they were trying to achieve, and I'm not sure what they did. So I'm going to have to go over the wiring of this thing, and we've got a pair of 100 microfarad caps here that we have to replace, and we have those right here. So we've got a little bit of work to do. It's a really simple radio, and we've got a bunch of these solar caps that we need to change. But the main thing for me is I just don't know what was going on underneath this thing. So I'm going to get this all cleaned up, and I'll show you what that looks like when I have all this stuff connected and we do our first power on test. That'll be the next video. But I want to give you a demonstration of capacitive reactance so you understand exactly what I'm talking about. So what we have here is a way to experiment and test the theory out. So let's talk about what we have here. Let's get a little bit of a close-up. I currently have two non-polarized caps there, and these are basically 0.1 capacitors right here. So I've got two 0.1 capacitors. These two ends are tied together, and I've got one end here on a peak LCR 45, and the other end is here. Now these are going to be smaller than the ones I currently have in the in this radio. I've got 3.5, remember? So these are okay. These will work. These will demonstrate it. So these are 0.1s. So let's zoom in a little bit. Let's go to our menu. So we're going to work on capacitance, frequency. We're going to choose 1 kilohertz. And let's test it. And you'll see here, at 1 kilohertz, we have roughly 3.1 K ohms of resistance. That's pretty good. Let's go change it to 15. Changing the frequency, remember that? So let's go to capacitance. 15 kilohertz frequency. And now you'll see that we're getting 212 ohms. Big difference. So the frequency really made a huge difference on that one. If I were to use these caps in my radio, obviously it would be very different. So actually I just ran this through our calculator. So at 60 hertz with a 0.1 cap, we would end up with about 26K of resistance. So frequency changes it. Obviously that's the demonstration, and want to make sure that you understand how that works. And these LCR meters are really, really good. So let's get to the next section. Okay, what you're looking at here, and this is my Heathkit ET3300 laboratory breadboard. I love this thing. It's got built-in power supplies, so I've got 12 volts and 5 volts, so I can play with just about anything I want. What we're building here is a guitar pedal. Now, I know some of you probably won't be interested in this. That's why I'm not going to do a series on it. But I play bass. Those of you that know me know I'm a musician. I play bass. And one of the sounds that I've been trying to get is a distorted treble type sound. If any of you have ever listened to The Who, John Entwistle, who was their bass player, had a very distinct sound, and I love that sound, and I've been trying to get that and haven't found it. Well, with Brendan's help, we've got it here. And I'm not going to give you a demo of it yet until this is done. But essentially what we're doing is we're using an LM741 op amp. Okay? And essentially what's happening is our signal's coming in, it's going across a resistor, and it's going through the LM741 and coming out in the other end, and it comes out a little bit distorted based on a dropping resistor. Now, the dropping resistor right here is this potentiometer. It's a 1 meg potentiometer. And I found that the sound that I like actually is about 470 ohms. I'm sorry, 470K of resistance gives me the distortion that I need to come out of that chip. We've also installed some clipping diodes here. So clipping diodes are another way to achieve distortion. So it clips the signal basically. So we've got that set up here as well, and all of these are controlled with a pot. So that's what we're doing. Here's a little bit of a schematic that Brendan and I were working through. So here's the signal coming in. Here's our capacitor going through a resistor, going into the input of the LM741, coming out the other side on pin 6 and going out to the output. Here's the dropping resistor that we were talking about. So in this example, it's 220K. Mine is 470, but I've got a pot there so I can adjust it. And then pin 7 and pin 4 are the power, 12 volts in and out. And there's a whole bunch of other things. So the clipping diode portion looks more like this. This is on the output. All right, and there's a saturation knob, which is right here. And here's the clipping diodes. So that's what this looks like. So you know, if you're interested in this stuff, let me know in the comments, and I'll do a mini series on it just to show you what it looks like. But this is the other stuff that I'm working on as well. So this is fun, and obviously when this is all configured and done correctly, I will try to make a circuit board, because I've made a circuit board before. It's pretty fun, and build a little pedal out of this thing. Okay. So if you have any questions about that, let me know. Let me put this away and we'll wrap up. Okay guys, so that's a wrap for this video. So this is going to be our next project. Again, it's a Fada P28A P22. Looking forward to doing this. Let me show you the case real quick so you can see what that looks like. Let's move this aside. Here's the case. Let's pull that shut up. It's a nice little unique suitcase kind of deal. And you'll see it's got a dial glass in there, which we may have to recreate a new one. I've seen some really good videos on how to create new dial glasses. And we got our speaker baffle in here, and you know, this material is a little bit broken here, so I'm going to have to figure out how to clean it. And then looking in the back, got a nice leather latch here. And this is what we have. The radio fits in these slots, and then underneath here was meant especially for the batteries, all the batteries that this thing required. But we're not going to be using those. And we've got some bits and pieces in here that we need to put back together. We got the original knobs and all that good stuff. So this is what the case looks like, and there's a loop antenna right here in the back. So that's good. So so that's our next project, guys. So that's about it for now. I will be back in our next episode, and we'll have some of this stuff working, and I'll demonstrate how that capacitor works for dropping our voltage, and if it did work. And we'll measure it, and I'll show you guys all that stuff that you need to know. All right. I hope everybody has a great Sunday. I'll see you guys soon, and let me know in the comments what you think. And if there's anything else you want to see, let me know. I love working on anything, so if you have any suggestions on what I can work on, let me know, and I'll be happy to put that into a future video as well. Have a great day, everybody.